Greetings and welcome to our presentation on maximum likelihood and Bayesian parameter estimations. First of all, when designing an optical classifier, it is necessary to consider two conditions, that is prior probability and class conditional density. However, in practice, we may not have complete knowledge of these conditions. This is where parameter estimation techniques come into play. The two most common techniques for parameter estimation are maximum likelihood and Bayes estimations.
Maximum likelihood estimation is a statistical method used to estimate the values of model parameters that best explain observed data. The basic idea of maximum likelihood estimation is to find the best parameter that maximizes the probability of observing a given training set under the assumption that the parameters are fixed but unknown. Maximum likelihood estimation is a simpler alternative to other techniques such as Bayesian techniques. The likelihood function is defined as probability of d given theta equals to product of I equals 1 to n probability of x sub I given theta, where d is the observed data, theta is the parameter being estimated, and the probability of x sub I given theta is the probability of observing the ith data point x sub I given the model parameters theta.
The formula for maximum likelihood estimation is theta hat equals ARG max of probability of d given theta, where theta hat is a maximum likelihood estimate of the parameter theta, and ARG max is an operator that returns the value of theta that maximizes the likelihood function. In practice, numerical optimization methods are often used to compute the ARG max. To simplify the calculation and reduce the risk of numerical underflow or overflow, it is common to take the logarithm of the likelihood function. The log likelihood function is defined as log of probability of d given theta equals sum of I equals 1 to n log of probability of xi given theta, where n is the number of observation and xi is the ith observation. Maximizing the log likelihood function is equivalent to maximizing the likelihood function, since the logarithm is a monotonic increasing function. Therefore, we can use the same optimization algorithm to maximize the log likelihood function as we would use to maximize the likelihood function.
Bayesian estimation is a statistical method for estimating unknown parameters of a model, where the parameters are treated as random variables with prior probability distributions. So after observing data, the prior distribution is updated to a posterior distribution using Bayes' rule, which combines the prior distribution with the likelihood of the data. This posterior distribution represents the updated belief about the parameters given the observed data. Bayesian parameter estimation is the process of using Bayesian estimation to estimate the values of the parameters of a statistical model. This allows us to make more informed decisions based on our updated belief about the parameter values. So the key terms include prior distribution, posterior distribution, likelihood, Bayes' rule, and random variables.
So next will be the Bayesian estimation. So it calculates for the probability of omega I given to x and d, and we assume that the probability of omega I given d is equals to the probability of omega I, so we will get this formula at the end. So next will be the Bayesian parameter estimation. So it calculates for the probability of theta given d, which is the posterior distribution, and also it uses the likelihood function and prior distribution to calculate the posterior distribution. So for the theta, it represents for the parameter vector, and this is the random variable. So for the d, it represents for the dataset, or also known as the training samples. So after we know the basic, this will be the Bayesian predictions formula. So we substitute these equations into the formula, and then we will get this. And then since the selections of x in dataset is done independently, so we just assume that it is the probability of x given theta. And then after that, we substitute inside, and we will get this formula for the Bayesian prediction.
Now that we are explored both maximum likelihood and Bayesian estimations, let's summarize the difference between these two methods. The difference between the maximum likelihood estimation and Bayesian estimation is the parameter vector delta for MLE is to be fixed, but for BE is to be random variables. MLE is finding the values of the model parameters that maximize that likelihood function, but the BE is specifying the values of the model parameters and observed data to obtain a posterior distribution.